Let's now demonstrate how machines can learn. I'm going to use an audio example because the relatively low dimensionality of audio makes it easier to visualize some of the math. This waveform represents Sarah from the Signiant data science team saying, "Hello." Let's zoom in on a portion of this signal. The signal has been filtered to remove frequencies above 4.4 kHz and sampled at 8.8 kHz to produce the orange samples. If we convert back from digital to analog by playing out the square wave formed by the orange sample, we're going to get Alias energy transfer to higher frequencies. Energy transfer is proportional to the sinc function, shown in orange in this frequency domain graph. We can accept this distortion of our signal, or we can apply a filter to get back the original signal. This filter has been derived by science, but can a computer learn this filter? We can apply a filter using convolution as discussed previously, as part of a multi-bitrate digital filtering technique to upconvert the signal from 8.8 kHz to 44 kHz. So zooming in a few more times, we have two sets of numbers, our input and our desired output, both sampled from the original signal at different rates. The lower frequency signal has been extrapolated to have the same number of points as the higher frequency signal. We're going to use convolution to apply a digital filter to upconvert from a base sampling rate to a sampling rate 5 times higher. So the question is, what weights should we use? Science tells us the answer, but let's try to learn it. Let's start by randomly guessing some initial weights and applying these weights to the orange points using convolution to produce the black points. We can now see how wrong our result is by comparing the black points to the blue points. Now let's randomly make small changes to the weights and see if we get a better result. If we get a better result, we keep the new weights. If we get a worse result, we keep the old weights. And we do this over and over again. As we iterate, we get closer and closer to the result predicted by years of science. We can get way more efficient here than random guesses. Specifically, if we create a differentiable function that calculates the wrongness of our answers, we can use calculus to inform our steps rather than making random guesses. But this introduces a lot of complexity explaining the details of math that amounts to an efficiency improvement, albeit a very necessary efficiency improvement. The key point is that with a relatively simple program, 20 lines of code, making random guesses, and about 10,000 example input and output points, we can replicate the result produced by years of science. This result seems to match our mathematical intuition and isn't that hard to trust. So let's talk for a moment about why deep neural networks don't learn weights that match our mathematical intuition. Starting with some digital signal processing first principles, we know that for this audio upconversion example, we need to apply two filters: a frequency-specific amplifier and a low bandpass filter, shown here in both frequency and time domain formats. So we can multiply the filter components in the frequency domain or apply convolution in the time domain to get our desired filter. So why won't a deep neural network with a hidden layer learn these mathematically intuitive component weights? Although there's only one result for the convolution of these two composite filters, there's an infinite number of possible decompositions of the resulting filter. Let's look at a factoring problem as a simpler analogy where it's easier to see the underlying concept. Given the number 100, most people will immediately and intuitively say that 10 is a factor. In fact, all of the factors of 100 are relatively intuitive. Even when we look at a large number like this one, we will say that 110 are factors. This is because of the 2 zeros at the end and our familiarity with decimal numbers. But if a computer produces the last two numbers, is it wrong? I'll give you a second to do the math, and no doubt, with some quick math in your head, you've determined that these are indeed factors. So to say that we don't understand how neural networks work is misleading. We can say that the transformation and pattern matches they arrive at aren't mathematically intuitive, but this is very explainable. Let's look at another transformation example. Let's consider a simple one input, one output linear regression. This could be represented as a single input, single output neural network. We can fit a line to map x to y with a y-intercept and a slope, or a bias and a weight. but it looks like there might be something else going on in our data that a simple linear regression isn't catching. Instead, if we transform x to x squared and fit a line, we get a much better result. We accomplish this through manual tinkering, but transformations can also be learned. Trying to map x to y without a transformation is the equivalent in the digital signal processing world of trying to process a signal modulated on a carrier. Multiplying one signal by another, i.e. modulation, is a non-linear process. To process a modulated signal, we typically demodulate it first. One way of demodulating a signal is to use a low bandpass filter that filters out the higher frequency carrier. And we know this filter can be applied using convolution or a multiply and sum operation. Perhaps stating the obvious, but there are a lot of applications where the order of the input data points contains important information. The frames in this video, played in this order, look like a single me, whereas the frames of this video played in this order look like 4 of me, moving 4 times as fast. Monkeying with the order of the pixels produces even more unsettling results. These sound waves, converted to spectral densities and then to text, have the exact same words, yet the two sentences have the exact opposite meaning. Hopefully everyone is thinking the former and wouldn't want to be misinterpreted as the latter. So we've established that the order of inputs contains information. The good news is that we can also use this to our advantage in multiple ways. There are 676 pixels or inputs in this image. If we fully connect these inputs to another layer in a neural network, we have almost 500,000 weights in our model. But we know that pixels are most relevant in the context of the pixel next to them in time or space. We could allow our network to learn lower weights for connections between pixels that are further apart. Alternatively, we could take advantage of this knowledge and only connect pixels or nodes that are close to each other in one layer to common nodes in the next layer. Furthermore, if we use a common set of weights across all groupings of adjacent pixels, we can not only reduce the number of weights we need to track, but we can also produce better results. To build some intuition around this statement, let's go back to edge detection filters. People familiar with image processing know that we can use convolution with a convolutional kernel or filter kernel to sharpen, blur, and otherwise transform images. That is, we can multiply values for a set of adjacent pixels with a specially designed matrix of numbers, the filter kernel, and sum up the results to get a value for each pixel in a resulting image. In this example, I've applied an edge detection kernel to a grayscale conversion of the video clip we saw previously. We can see my skier outline disappearing in the snow and the outline of the trees panning across the scene. Although it's very unlikely that a neural network would learn the weights of an edge detection filter, it's reasonable to assume it would learn weights that transform images into patterns that allow certain attributes to be more easily matched. So a quick recap of everything we've learned so far. Neural networks and digital signal processing techniques use common math. This math can be used to match patterns, and this math can be used to transform data into new forms that highlight different attributes of the information. We can learn these weights from examples using an evolutionary approach that incorporates simple random guessing. Although techniques derived through calculus, like gradient descent, are much more efficient, but I promise just high school math. Neural networks often learn in unintuitive ways, but this doesn't mean we don't understand how they work. In media and in digital signals in general, order matters. Order contains information, and order can also be used to optimize how we build media-specific neural networks.